Okay, so wavelets. Try and achieve a compromise. They always mean to obtain good temporal resolution in the high frequencies and good frequency resolution in the low pass band. In particular, you can, given an original signal, which I will again assume to be of length 8 here. Actually, I need a bit more space. You can pass the signal through a high pass filter. I'm using H here for high pass and G for low pass. But note that other people use the convention, which is the other way around. And if I do so, I will somehow split my signal into parts. So again, here is space or time. And here is frequency or scale. I will somehow divide my signal. This division could be really hard. Excuse me. This could be a hard partitioning if I use a perfect high pass and a perfect low pass filter. So a filter whose transfer function is exactly 0 in the other band. But in most cases, such a filter will just mean more of the resulting energy is in the low frequency band or is in the high frequency band. And there will be some bleeding between the two. So at this stage, I could still so in principle, I could still keep 8 samples because, you know, I convolve my original length 8 signal with a high pass filter and my result is again of length 8. I could do that, but if I do so, I will end up with a redundant representation. So instead, I will downsample by a factor of 2, meaning I keep only 4 samples up here. Same for the low frequency band. Now note that this is associated provided G and H fulfill certain conditions. This is not associated with any loss of information, this downsampling, because, let me try and explain in terms of pictures again. If I look at the spectral density of my signal at this point, and I'm assuming here, if I assume a perfect low-pass filter, then this perfect low-pass filter will leave everything in here intact and will set to 0 all higher frequencies. And here is due to the periodic boundary conditions, this continues. And if I now downsample this perfectly low pass filtered signal by a factor of 2, what happens is the following. My original low pass filter does this, but now my unit cell has shrunk by half. So now the periodic boundary conditions mean that the spectral density of the next filter, excuse me, this was not very symmetrically drawn. Continues exactly here and so on. However, there is no overlap between the spectral densities due to this downsampling because this filter set the spectral density up here where I draw the red lines exactly to 0. And a similar argument holds for the high frequencies. So this was the perfect high pass filter. And if I now downsample by a factor of 2, the part that was previously here is now located there, and the part that was previously here is now located there. And here are again my periodic boundary conditions. And I have not created any spectral overlap. So this illustration was for perfect high pass and low pass filters, but for suitably constructed filters G and H, this works even when they're not perfect high pass or low pass filters. All right, so I have created the first partitioning into a lower and a higher frequency band. And the result here I will call, following the convention in the field, the details at level 1. And actually I leave them unmodified. So these are the details at level 1. Now the remainder here, the low frequency, I'm going to split again. So I want to add an extra split here, which I can achieve by using the same high pass and low pass filter as before, but now on a much shorter signal, of course. So those would be the details at level 2. And then I'm going to split one more time. Which gives me the detail at level 3, and the remainder is called the approximation. Or in more detail, this is the approximation at level 3, whereas the result that I've gotten here would be the approximation at level 2, and there would be the approximation at level 1. And on the right-hand side, I'm drawing the frequency axis. Where this is pi. I'm only showing the positive half axis here. So the detail at level 1 amounts to all the higher frequencies. The detail at level 2 amounts to these frequencies. Detail at level 3 amounts to those frequencies, and the approximation to the remaining low-pass signal. And then the thing is symmetric around 0, so here on the other side I would again have the details at level 3 and so on. Okay, and this plot that I've shown here matches the one that I've shown above. So if I take this here and rescale it properly, it will match what I've drawn on the other side. Something like this. The aggregation time, can you explain again what? So I have a higher resolution, a higher temporal resolution in the band up here. So here I have a temporal resolution of 4 samples, whereas in this band I only have a temporal resolution of 2 samples. And down here as an extreme, I have no temporal resolution at all. And the reason is the Heisenberg uncertainty. So in a way, if I represent such time frequency atoms by Heisenberg boxes, then the uncertainty relation tells me that their area must always be the same. And let me try and explain again. So, I've tried to color code here what's going on. So this was my first split into a low and a high frequency band. And this split number 1 was accomplished by using the high and the low pass filter on the left-hand side. Now, after downsampling by a factor of 2 and having a signal of original length 8, I'm left with just 4 samples here. Now, At this stage, if I took the approximation at level 1, the bottom part, or if I had stopped here, the bottom part would have looked just as the top part, and I would have obtained something looking similar to the short-term Fourier transform. So this would have been the result. But instead, I decided to split again, shown here, using this split number 2, by using a second pair of high and low pass filters. And the downsampling here by a factor of 2 means that from 4 samples I go to just 2 more. And then there's this third split here, which is accomplished by using these high and low pass filters. So overall, if you draw this for not just 8 but a few more samples, you get a picture as shown here, where in the this would be my details at level 1. So I have great temporal resolution, but poor frequency resolution. And in wavelet transforms, I willingly make this user decision, or it's a design choice, to say that in the high frequencies, I want good temporal resolution even while sacrificing frequency resolution, because note how large these boxes are. So information here is poorly localized in frequency. But for the low frequencies, I want to have good frequency resolution, even if this means I lose location precision. And the motivation for this are, these instruments here that I want to localize high frequencies in time, and I want to find low tones more, or I want to characterize low tones more in terms of their precise frequency than in terms of their precise onset. And here on the right-hand side, I tried to show on this frequency axis, so this is a axis here of frequencies starting at 0, where these different filter banks leave the energy of their signal. And all of this is easiest to imagine if we assume that we have perfect high pass and low pass signals. So what I try to show it, this corresponds here, this corresponds there. Okay, this is the correspondence that I meant to show. If we had perfect bandpass filters, then the filter response of this first filter here would look like this. The first high-pass filter would have a response of 1 here and of 0 everywhere else. And the second filter would have a response of 1 here and 0 everywhere else. And the third one would have a response of 1 here and 0 everywhere else, and so on. In fact, such filters exist. They are called the Shannon wavelets, or the sync wavelets. However, given the Heisenberg uncertainty, these results from these wavelets are very well localized in frequency, but poorly localized in time. And this is why in practice one tends to prefer filters that look like this. So we have, in practice, one would choose a high-pass filter whose response decays towards the low frequencies, and then a second filter with a response something like that, and a third filter with a response somewhat like this, and then finally a low-pass filter that collects all the rest. And again, note the symmetry here is my, excuse me, here's my zero frequency, and up there is pi. So this whole thing has to be periodic. Now the condition so that we don't lose any of the signal or any of the energy is that the modulus squared of these transfer functions must add up to 1. Okay, because then they represent a partition of unity, and I neither gain nor lose any information or energy. No, it's nothing to do with real or imaginary. Okay, so here I'm showing you, you know, because these scribbles of mine are perfect hard to look at. Here I'm showing you a real example of the transfer functions of a wavelet transform. This is at the top here. This is what you would get the level 1 details, the transfer function of that. This would be the level 2 details, level 3 details, level 4 details, level 5 details. Of course, this works for signal. This only works for signal that has more than 8 samples. Because with 8 samples at level 3, I've already exhausted my signal. And not shown here, look at this gap here in the transfer functions. So what's not shown here is the approximation or the low pass result that we keep at the end. And all these details plus the approximation, all of them taken together, they must sum up to 1. So this picture here with these iterated filter banks, can you see the correspondence of the left-hand side of this picture with the right-hand side? Sort of. If not, then please ask questions. Yes. So this entire plot on the left-hand side refers to the time domain. So I'm simply using, you know, it's easier to say what a low-pass filter looks like in the frequency domain. A low-pass filter is a smoothing filter. And a high-pass filter, well, is something that looks rougher. It kills all the low frequencies. So for example, we know that we want the high-pass filters or their transfer functions to have no DC term. And because we don't want them to have a DC term, it means that their integral or their summation in space must be 0. And in fact, this is one property of wavelets, that if you take their average value, it is 0. So the wavelets are all, a wavelet by itself is a high-pass filter, but if you only apply it like here to the output of a low-pass filter, then that gives you a bandpass filter. And this was the image that I've well, sketched here in the middle, but also what you've seen down here, that we have here a variety of, by arranging these repeated filter banks in a sort of tree structure, we get out a high-pass filter, and then a number of band-pass filters and a low-pass filter. So here, this is not implemented in terms of short-term Fourier transforms. The proper label on this vertical axis here is no longer frequency, but it's scale. But what I can do, and perhaps that helps answering your question, is I could look at this stage at the filter responses that I get. And I would obtain an image that looks like this. So I have, if I have here scale versus time or space. So I have a single partitioning in high versus low pass. And after downsampling my length 8 signal by a factor of 2, I get 4 responses. Now at this point here, I leave the coefficients in the upper half untouched. This is what I'm meant to indicate with this arrow here, you know, that nothing is happening. And at this stage, however, I have split my bottom part again in the high and the low frequency contribution. And after the downsampling, I'm still left with a total of 8 filter responses here. And then there's this final stage where I've left the first level of details alone. I've left the second level of details alone, but I've split the final this part here into another high and low frequency part. And for a signal of length 8, I can no longer continue. So I've done this 3 times, and 2 to the power of 3 is 8, which shows you also this n log n complexity that you have in this entire procedure. Actually, there are even more efficient implementations, and you can do it in just O of n. Yes. Yes. It's let me call this a filter response or so. Yes. Or you can call it coefficient. Yeah, that's good. Mm-hmm. No. No. So no Fourier transform here is required. So so I have my signal, and I convolve it with filters, and the resulting number is already what I put in these boxes here. Yes. Yeah, these filters G and H are just convolution operators. I convolve the signal, I convolve my signal with a certain filter, with a wavelet filter, and I store the resulting coefficients. So these are the wavelet coefficients, and they are the representation of my signal in this new domain. The maximum frequency always depends on the length of the signal. The decision I can make is at which point I want to stop this recursive partitioning of the lowest band. So I can also you know, I could have stopped here after just 2 recursive partitionings if I had wanted, rather than 3. This is the choice that I have. So to how many levels, I always start at the finest level, at level 1, but then I have the choice to what coarse scales I want to continue. Yes, you could do that. So let's say if I want to understand the effect of this filter here. So this green, let's say, if I want to understand the effect of this, which corresponds to that coefficient, I can obtain that by G followed by, I can write that formally as the downsampling of 2, I can formally write, I think, as a convolution operator. convolved with another. So because I'm not sure if I can write it a convolution, I'm just calling this operator O. So the G and the downsampling together, and I can now just convolve O with itself 3 times, and that gives me the effective filter that gave that result. However, the cascade that I've shown here is just an efficient way of achieving the same result. Yeah, computationally efficient. You simply omit every other. No averaging, nothing. You just omit. Yeah, this is the definition of downsampling. Yeah. No. So thanks to these periodicity and so on and these arguments that I've shown here, it does not introduce any errors. So approximation is qualitatively different in the sense that it is a low-pass filter and it has a DC term, and the others are band-pass or high-pass filters and do not have a DC term. I've plotted here the transfer functions, and to stress this or to account for this fundamental difference, they also have different names. So the remaining approximation is the transfer function of what's called the scaling function, whereas all the others are called the transfer functions of the wavelet. So wavelets are these bandpass or high-pass filters, and scaling function, well, wavelets are high-pass filters, and scaling function is the complementary low-pass filter. So, there's no magic. These are all convolution filters, but there is a distinction between the two. Yes. You cannot use arbitrary functions G and H, but they have to fulfill some specific mathematical properties. Okay? And if you want to use this non-redundant wavelet transform about which I've been talking all this time, then you want to have a unitary transform. So let me write that down. So for the discrete wavelet transform, requires a wavelet psi of t such that its scales and shifts form an orthonormal basis of the space of square integrable functions. And this unitarity constraint you can either express in the Fourier domain, or you can express it in the spatial domain. And so if you use 2 indices, an index j for the scale and an index n for the shift, where both j and n have to be integer numbers, then you want these psi j n of t to offer you a orthonormal basis. So let's say jn with psi lm. And this is the requirement that you have to fulfill. Now essentially there are two wavelets that fulfill these properties that are easy to design, and the others need a lot more math. One of the easy examples is the Haar wavelet that you've probably heard about. Shown on the left are the basis functions. Shown on the right are also the basis functions, but such that you can actually read the symbols. So what you have here first is the scaling function, which is usually written with a phi, and the rest are all wavelets that are traditionally written with a psi. And now you see these here, for example, are the four wavelets that are associated with, in the length 8 example that I had shown, they are associated with the details at level 1. And then these here are associated with the details at level 2. And this is the detail at level 3. And on the top is the scaling function, the low-pass filter, which again is qualitatively different because these wavelets, they always have 0 average, so they have no DC term, whereas the scaling function has a DC term. Now this Haar wavelet is as simple as it gets. This is just a length 2 filter with coefficients +1, -1 at the finest scale. And it's easy to see that they are orthogonal to each other. So within one level, just by shifting, you can see that they're orthogonal. And it's also, if you compare, let's say, this wavelet here with that one there, it's also easy to see that they're orthogonal because, the one wavelet here is constant positive and the other one is positive and negative. And if you convolve these two, you get out, or if you take the inner product between these two, you get out 0. So this is a wavelet that's easy to design. It is very well localized in space. It is one of these limiting cases of the Heisenberg uncertainty because it really has it really has finite support. However, it is poorly localized in frequency. So you see that the wavelet has these discontinuities, these jumps, and such jumps always make for a Fourier transform that decays very slowly with high frequencies. Yes. Yeah. Scale is the opposite of levels. Yeah. Mm-hmm. Okay, so this is one easy class of wavelets, and the other easy class of wavelets is the complementary. This is the Shannon or the sinc wavelet. which is not well localized, I should say perfectly localized in frequency. But it's poorly localized in space. So that's a bit of a repetition here. If I look at these transfer functions, if I use this sync wavelet, then this would be the details at level 1, or the transfer function of the details at level 1. And that would be the transfer function of the details at level 2. That would be the transfer functions of the detail at level 3. And now I can continue this as long as I want. And when I'm getting bored, I simply leave the rest as approximation. So this is the low-pass filter that's complementary to the rest. Yes, it's always divided by 2. Yeah? So this was, if this is pi, then this is pi half. This is pi quarter. This is pi over 8, etc. So you are asking why divide by 2? I had a binary tree, which I was building. And so let's see. Yeah. So at least that doesn't work with this scaling relation that I had written here. So you could have a wavelet that always, let's say, shaves off not the top half, but the top third. Yeah, I think that's possible. I think you could do that. Yeah. Yes, there are hundreds of wavelets, or let's say dozens at least. So the Shannon or sync wavelet, I've shown it here in terms of its transfer function. In terms of, well, the filter that corresponds to the approximation is just a sync. And all these detail filters are sync at one frequency minus sync at another frequency. So generally speaking, these are fairly smooth bandpass type. These are perfect bandpass filters, and that one here is a perfect low-pass filter. Okay, so these are two extremes, but probably not the best. So you could ask, what is the best possible wavelet? And now beauty lies in the eye of the beholder, because there are many different criteria possible for what it means to be best. But one good candidate are the Daubechies wavelets. I'm stating here without proof that they have the minimum length of the filters in the spatial domain for a given number of vanishing moments. So if you have a wavelet with n vanishing moments that is orthogonal to polynomials up to degree n minus 1. So in other words, if you have a relatively smooth signal, it would be nice if you could represent it in terms of coefficients only at higher levels of detail and in terms of the approximation. And if you take this particular criterion, you want the minimum size filters for a given number of vanishing moments, then the single best possible answer is unique, and those are the Daubechies wavelets. And they're actually a generalization of the Haar wavelet. I don't have a plot anywhere. So let's see. The 2-tap Daubechies wavelet, which is not shown here. I will share these figures with you, okay? Because I know you cannot copy them down by hand. So on the top is the scaling function, which for the Haar wavelet is just the box. And down here is the wavelet, which for the Haar wavelet is this. And p equals 1 means that any function which is piecewise constant, you can approximate in terms of, can conveniently approximate in terms of such a Haar wavelet. However, if your function has more smoothness, then you will want to use such a higher order Daubechies wavelet, which for a smooth function will mean that all the coefficients will be restricted to the high levels or to the small scales. Well, different conventions how you count scales. But the price that you pay is that these filters become longer in the spatial domain. So it's a bit more costly, and it starts to be less well localized in space or in time. Yes, they are analytically calculated, and so these Daubechies wavelets were the first ones, were the first continuous functions that were known that still fulfilled these orthonormality properties. So if you take this funny continuous function and scale it by 2, it's orthogonal to itself. Yeah, and you see that it has these quasi-fractal properties, and so this continuous version here, Wetterli, from whom I've borrowed these figures, says it's a fundamental link between discrete and continuous time. These continuous versions you obtain in the limit of applying this filter repeatedly to itself. So this is the D4 filter. So this is what previously I've called the high pass filter H. And if you now use this filter repeatedly on itself, then you get these smoother and smoother versions, and in the limit you obtain this continuous wavelet here. Yeah, this is the initial shape. Exactly. So it's called D for Daubechies and 4 because it's a tap 4 filter. It's not symmetrical, no. It matters, and even more so, these discrete wavelet transforms are not shift invariant. So if you take your signal, let's say with periodic boundary conditions, and you compute this wavelet transform, you get out a set of coefficients. And if you shift it by 1 periodically, you get out different coefficients. So unfortunately, these discrete wavelet transforms, they are not shift and not translation invariant. And you've noticed, yes, they are not symmetric. You can buy symmetry, but then you have to give up orthonormality. And then you need to use so-called bi-orthogonal bases, which are a bit more complicated. It's nice to have, but there's no compelling reason why you must have symmetry. Okay. So, and yes, you've mentioned there are other wavelets. There are literally hundreds of them. There's a website that enumerates a few of them, and they all have some beneficial properties. Some of these are defined for images rather than 1D signals. Okay, so that's a discrete wavelet transform in 1 hour. That's a bit of a tour de force, but you can also read the 1,000 pages book by Malat. No, seriously, questions? That's for the exercises. No. It's okay. So the question is, how does it look like concretely? You take a you take given a signal, you take a wavelet like this one or like a Haar wavelet and say this is H. And then you need the corresponding scaling function G. And then you really follow this tree that I've drawn. So you take your signal and you convolve it with a high pass filter, you convolve it with a low pass filter, and downsample the results by 2. These are detailed instructions which everyone can follow. Actually, rather than convolving and then downsampling, you can make this into a somewhat faster operation. So using just one operator here rather than a sequence of 2. But, I've taken a signal, I've taken a filter, and so what I get at this stage is just a convolution. The signal convolved with my filter. And then at this point here, well, I've left away every other result, and that already has given me the coefficients up here. Oh, sorry, when I say signal, I mean a vector. So my signal is a vector, and after convolving it, this is still a vector. So it's a circular convolution using periodic boundary conditions and so on. This is still a vector. And then after downsampling by a factor of 2, it's a vector with half as many entries. And those are the entries that you have up here. Now, in the spatial domain, yeah. What I've shown here is just a fancy arrangement of these coefficients in a way that is more, well, intuitive, perhaps. Yeah. No, we no longer have the notion of frequency. We here have the notion of space and scale. And given this wavelet, this is the content of the signal at these positions in space and at that scale. That's a concrete result. Okay, so I've only talked about the forward transform. Now for the backward transform, I need to do the opposite of all of this. So, take this thing here, mirror it on the right-hand side, replace downsampling by upsampling, and you have your inverse discrete wavelet transform. This is often shown diagrammatically like here on the right-hand side. I've chosen a somewhat different representation to stress this, hierarchical decomposition of always the coarsest parts of your signal. But so this is the signal here, and that is its wavelet transform. And here you can put in the wavelet transform and you get back out your signal. Yes, if you invert your, yeah, if you flip your signal, then you can correlate rather than convolve. They're almost the same. Okay, now the point of wavelet transforms is not, just to do a transform and to do it back, because you have, of course, not gained anything. So the magic is that this wavelet transform space is very well suited for denoising and compression tasks. All right. You want a picture. So why bother? It's always a good question. I will, in the remaining time, first give you a brief look at what can be done in this wavelet transform domain. And I will then, because it's a course on image analysis, talk about the 2D wavelet transform, and will then spend as much time as we have to give you actually the mathematical background of the results that I have on this current slide here. So again, these are pictures from the book by Mala. And on the left-hand side, you see first a toy signal, which has a couple of discontinuities. In the middle, you see a compressed version where the 15% largest Fourier coefficients were used. And no, it's not the largest, it is the 15% lowest Fourier coefficients. So the 15 lowest frequencies were used to reconstruct the signal, and you see that we have these Gibbs oscillations here. So this thing here, you see we had a perfect step edge, and where there was a perfect step edge, we now have these Gibbs oscillations. Yes, lowest frequency, not lowest magnitude. Thank you. So, it gives you a rough impression. It's a low-pass filtered version of the original image. And down here you see what happens if you use the 15% Daubechies coefficients of the largest scale. So 15% largest scale Daubechies coefficients. Perhaps you can argue it's a little less ugly, perhaps not, but that's not the point. So this is not the final result. The more interesting thing is to not use the lowest frequencies or the largest scale coefficients, but to use the most important coefficients. And that's what you see on the right-hand side. So same signal on top. Then in the middle, it's wavelet coefficients using this particular wavelet here, Symlet 4 wavelet. And then here the 15%, let me put most important in quotes, coefficients were used in the reconstruction. Those 15% are the ones shown here. And, at least at this quality of the plot here, I would say the result here is, it's indiscernible, the differences. And we've just used 15% of the numbers. And this is, of course, what you want in lossy compression, such as JPEG compression of images and such, to use just a fraction of the storage and have no perceptual or very little perceptual difference. Yeah, this was the input signal. This is reconstructed using the 15% most important coefficients, and here in between we see the discrete wavelet transform. No, the Symlet 4 coefficients. So those coefficients that were used here in the discrete wavelet transform. Yes, yeah, it's a different wavelet family that's being used. And, unfortunately, I don't have a comparison image here reconstruction using the 15% most important Fourier coefficients, but I conjecture that the result would look a lot worse because when I eliminate some of the plane waves, they no longer interfere constructively and destructively at the right places. So I might mess up my signal more. And I regret that I don't have an image to illustrate that effect to you. Okay. So, but this wavelet transform domain is particularly useful for the selection of the important coefficients, at least for images that have some sparsity or some regularity. And different wavelets are ideal for different types of sparsity or regularity. And if time permits, which I'm starting to doubt, then at the end of this lesson I will give you the math or the rationale behind this coefficient selection. But for now, I want to talk about 2D wavelet transform, where the same kind of coefficient selection can be used. So you remember the scaling function and the wavelets, and this is now reciprocal space. So this would be 2 pi times k1, which is here called omega 1. And this would be 2 pi times k2, which is here called omega 2. So the scaling function, as can clearly be seen, is a low-pass filter because it has all its energy centered here at zero frequency, somewhere in the middle. And then we have different high-pass filters. They are high-pass in different directions of space. And the reason for this particular shape is that it is desirable to use separable transforms, which I will try and explain in this image. So let's say I'm starting with the complete image, and I'm using first my high-pass filter in horizontal direction. And now I need good terminology. I don't see good terminology anywhere. So let's say I'm using the high-pass filter in X direction, and I'm using the low-pass filter in X direction, and then I am subsampling by 2. Well, let's look first at the high-pass filter. So at this point here, I have the entire image, or here in reciprocal space, I have this entire domain. Now, after using a high-pass filter and a low-pass filter, I get the following. I get the, okay, let's say this was direction X and this was direction Y. I get the high-pass result here. This is black. And I get the low-pass result there. Okay. Now, however, we want to run a 2D transform. So I can now run, in addition, a high-pass filter in direction of Y and a low-pass filter in direction of Y, which, if I'm going to color code, is going to give me this region here and that region. Soon running out of colors. Okay, and let's do the other one also. I want a high pass filter in Y and a low pass filter in Y. And now come the really fancy colors. Let's have so I was low pass in X and high pass in Y, which is this color here, or this area of Fourier space. And I'm left with this one here, which is that part. So, you know, at this stage, I have these four regions: the blue, the green, the purple, and the yellow. The yellow is low pass in both X and Y directions, so this is an approximation at level, well, let me call this 1. These would be the diagonal details. These would be the horizontal details. And these would be the vertical details. All at level 1. Now, if you want to do this recursively, we need to take the current approximation and further split it up. And I won't do it now, but I could draw another tree here, which is actually what has happened here in the center of my plane. So you see that I have here another diagonal detail. I have another horizontal detail. I have another vertical detail. And I have, perhaps there's another fancy color left. We haven't used that one yet. And I have my new approximation, which is here an even lower pass image in the very middle. Okay. My most colorful drawing ever. Does that make sense so far? So the beauty is we've used just 1D wavelet transforms to obtain the wavelet transform of a 2D image. But what does it mean? So I have another picture of the same thing. This is what I call, so this is the entire frequency plane. These are what I call the diagonal details. These are what I call the vertical details. These are what I call the horizontal details. And this here is the approximation, which can be further decomposed. If I had thought of it previously, I would have taken an image of these Russian, what are they called? Matyushka puppets, you know, where you have one inside the other. You know what I'm... Matryoshka, thank you. That was very nicely. Okay, thanks. So this is what's happening in principle. Let's look at this in practice. What you see here, again, a picture from the Malab book, is a way of rearranging these things in the spatial domain into images that a human can look at. So these diagonal details here taken together encode an image. And the image encoded by these diagonal details can be shown here. We also have an image encoding vertical details, which happens to be shown there. We have an image encoding the horizontal details, which happens to be shown here. And then it goes on. So the next level diagonal is here. the next level vertical is there, the next level horizontal is there, and then actually there's another level of approximations which I'm not showing, but look, here are the actual images. So here is the famous Lena image, which you see here in only its approximation form. So very strongly low pass filtered, which means it can be represented in terms of very few values or in terms of few pixels. This is the approximation that's left. So this is the approximation. And all the rest are the details at those various scales. Here are on the right-hand side are the horizontal details. So you mostly see an edge, you know, where, let's say, where a face ends. Here are the details for the vertical details. So you see where a shoulder, for example, starts. There are the details at, you know, the next higher level. Again, the horizontal parts and the vertical parts and so on. Perhaps more illustrative is the example on the right-hand side. So this was originally an image of a gray square on a black background. So the original image had exactly as many pixels as the full wavelet transform. So this was the size of the original image, and it showed a gray square on a black background. You know, just a toy image to show the effect of what this looks like in the wavelet transform. Let's look at the diagonal part of this. The diagonal details have non-zero coefficients only here at the corners of this cube. All other coefficients are exactly zero. Now this is an invitation to compress, okay? Look in how few bits you can store this diagonal detail image. Then up here are the horizontal details. So we have a white to black transition for the one side of the cube and a black to white transition for the other part of the cube. And again, all other coefficients are zero. Then here are the vertical details, where again, most coefficients are zero. And then this thing repeats at the other scales. Again, here is the approximation, which is a very strongly smoothed and subsampled version of the original image. Now, if we want this, so going from right to left was done by means of the discrete wavelet transform, here in 2 dimensions. And as long as we store all coefficients, we can go back with no loss of information whatsoever. If we now start eliminating small coefficients, actually for this toy example here, if I just omit the zero coefficients or if I don't store them, you know, I still lose no information. But if we look at Lena instead, here there are, so if I plot a histogram of these coefficients, so here is the number of occurrences and here is the magnitude of these coefficients, then I will have a few coefficients that have large values, but most coefficients, you know, my histogram, I have to break the y-axis here, most coefficients will have values very close to zero. And I can now make an approximation and say, look, I'm just going to discard all coefficients that have very small values, and I'm going to replace them by straight zeros, which allows me to do efficient chain coding or so of the remaining ones. And in this case, if I then transform back afterwards, I have, of course, lost some information. However, the information loss may not be perceptually significant. And this is exactly what's happening in this JPEG 2000 compression standard, which is based on the wavelet transform. Now, denoising is a cousin of compression, and I show an image here from open source software called DigiCam. They have wrapped a piece of code that is distributed with GIMP, the GNU image manipulator, and you see on the left hand a noisy image. You see the Bayer pattern and all, and on the right hand side what you get if you discard some fraction of the wavelet coefficients. So you see some slider here where you can adjust a threshold, and then you get out a baby with a much healthier skin. Beauty of signal processing. No? Okay. Go ahead. So I'm not going to say how it's actually done because it's full of very, very smart details. Yeah? But I'm going to give you an impression of how it's done. And let's say that these are the Fourier coefficients, and most of them are very tiny. I'm now, the line that I'm drawing here is, let's say, one line across this set of the diagonal details. And the coefficients, they can of course be positive and negative. So this is what it looks like. Now the approximation I make is to threshold. So to say I am going to discard all coefficients whose magnitude is below some value. So I'm saying that this is roughly the same as, I'm keeping only two coefficients here. That was the large one, and then there was a small one which was just above the threshold. I'm keeping just these two, and all the remainder I'm setting to exactly 0. Now this has, I'm not sure, 16 different numbers or so. And a simple chain coding, I think it's called, would be to say I have the number 0 4 times. So I need to store two numbers. And then I have a number which is, I'm making this up. This is perhaps 1.67. 1.67, which I have just once. And then I have the 0 another 4 times. And then let this be a 4.3. And then I'm having a 4.3, but just once. And then I have the number 0 another 7 times. And here I now have an interleaving these repeat counts. They are actually integer. And these other numbers, I could represent the 0 in a special way, but I'm going to not doing that now. The other numbers are real numbers, and storing this is less effort than storing the original amount of real numbers that I have in the original signal. Now beyond that, this might not be 1.67, but 1.67832. It might have very many digits. So beyond that, you will quantize. So you will round to some close by value, and you're not going to do this quantization one by one, but you're going to quantize pairs, triples, quadruples of numbers. And this is the kind of trick that's being used. So the thresholding is lossy, and then the quantization is also going to be lossy, and overall you're trying to squeeze the bit rate. So you're trying to get out images that are perceptually as good as possible at as low a fraction of storage space as possible. And it works quite well because we have so much redundancy in natural images. Okay, and the thing with the wavelet transform, that's actually the JPEG 2000 compression, but well, most applications still use JPEG, and JPEG is in fact built on the discrete cosine transform. So it uses a different transform, but then it also thresholds and vector quantizes and so on. So those ideas are the same. Okay. More questions? I have another image which perhaps helps understand what is visible where. So here you see the original image, and down there you see this funny composite image of the various details as well as the approximation. And here you, in the bottom right corner, for example, you see the diagonal details. And if you look at the original image and where we have diagonal details at a very, very small scale, it is essentially here and there and there and there. And this is exactly where you find non-zero coefficients. Then if we ask for very small vertical details, we find them mostly here and there, which is where you see coefficients with larger magnitude. Same goes for the horizontal coefficients. And now what's interesting is, as you see that in this test image, the spatial frequency is not constant. So as we move in towards the center of this test pattern, we get lower spatial frequencies. And these lower spatial frequencies are represented at these other scales. So for example, let me zoom in really far. If I'm now looking at the vertical details at this scale here, you see that at the very high resolution or the very small scales, the vertical details were at the very limits, at the very outsides of the circle. But now at this scale here, and there's a blow up shown there, the highest energy is more in the middle of this test pattern. Okay, so we have a direct reflection of the change of spatial frequency in the original test pattern, which means that different parts of the image get mapped to different parts of the wavelet transform down there. So if you are, the smart way to do compression is to keep just the large coefficients. But if you are happy with getting or with storing a lower resolution version of your image, then you can simply delete all the very high frequencies and you're left with storage, just a quarter of the original storage. But the much better way, as I showed before in the 1D example, is to not discard coefficients by scale, but to discard coefficients by magnitude and forget about the small ones. Do you have questions? Oh, so the development started with French mathematicians who called it wavelet in French, ondelet, and they simply called it that because you know that for each wavelet the DC term must vanish, so its sum must be zero. They always look something like this, like like a wavelet. This is why it's called that way. Yeah, and this has been a huge, this has given a huge boost to the signal processing dash mathematical community, because you have very deep mathematical concepts. I've alluded to some of them in the context of these Daubechies wavelets that make a link between the discrete and the continuous world, and practical applications on the other side. So this has been a very attractive area for applied mathematicians. All right, so I cannot give you the full mathematical treatment of the wavelet thresholding. So let me do just two things. One is to say that wavelets are not the end of the story. So if we look again at the tree of filter banks that I've shown, it looked like this. And I could go on with this tree. This was the tree of filter banks where I've always used a high pass filter and a low pass filter and a downsample, etc. Okay? And this amounted to a specific partitioning pattern of my frequency space, where I always insisted on having the best spatial resolution at the high frequencies and the best frequency resolution at the very big scales. However, coming back to my original motivation, or the picture that I showed at the very beginning of today's talking about wavelets, you know, the kind of partitioning that I've shown just now is not necessarily optimal for a signal like this one. So it seems attractive to adjust this tree of filter banks to the signal. And that is indeed done for so-called wavelet packets. So in a wavelet packet, for example, I can decide that I may want to split also the upper arm and, you know, this is completely general. Build any binary tree that you like. And you can well, think of the so let's say there was one node here and there was another node there. You can now think of the corresponding time scale partitioning. So the first one was a low and high pass filter. I then partitioned again my high frequency, and well, that's not a very interesting tree. Okay, we need to make it a bit more complicated. Yeah, no, that's correct. The tree that I showed could correspond, for example, to a partition like this, where now I have not shown the original samples. So each of these original samples now would have to have a same size so as to fulfill the Heisenberg uncertainty relation. Okay, so you can build more general decompositions. And the other thing I want to mention is that this thresholding of wavelet coefficients is closely related to the lasso. For those of you who've heard about it, so if you use, let's say this is the original coefficient, and this is the regularized coefficient, if you look for the transform that best matches your observed signal, while at the same time minimizing the L1 norm of all transform coefficients, then you get what is also called soft thresholding. Yes. So if I have the following task, I want to minimize the difference between my original signal and the inverse transform of some transform H bar that I'm looking for, plus a penalty on the L1 norm of this transform. So G is the observed signal. That's simple. T dagger is my inverse unitary transform, such as a wavelet transform, which is also given. Kappa is a regularization constant, which is also given. And it is this transform H circle which is wanted. And if you minimize this thing over H circle, then the result will be a soft thresholded version of the original coefficients, which is what I try to indicate with the red line here. So if I do not modify my original coefficients at all, then the regularized coefficient is the same as the original coefficient. And soft thresholding means I always make my coefficients smaller by an amount kappa, the same kappa that I had down here. If I put a 1/2 here. However, if the coefficients have been small, then I simply set them to 0. So this is what you see in this area here. This is called soft thresholding. And this problem here is known in the statistical community as the lasso. A good alternative to the lasso is Haar thresholding. Excuse me? That's the truncating thing. Yeah, so for the Haar thresholding, I keep the coefficients unmodified, except if they're too small, I set them exactly to 0. And if they're large enough, I again let them live unhindered. This is a procedure called Haar thresholding. And that's the one that was used in the examples that I've shown. Now, if you think it would be nice to have a compromise between these two, there's a lot of theory for that. Look at this curve here. So I have only time to show you the curve now. So asymptotically, it goes to the unmodified coefficients, as in Haar thresholding. But here locally, it behaves more like soft thresholding. And that is corresponds to the so-called adaptive lasso, which is a Zhu, I think, 2006 or 2008 paper in the, I think it was Journal of the American Statistical Association. A very important paper in the theory of regularization. So Much of this theory has been developed in wavelets by people like Donohoe. Independently, all of this regularization theory was studied by statisticians, by Tipshirani and many, many others. And actually, they turn out to be the same. This is a special case of the lasso, special because we have this unitary transform here, which makes for particularly simple formula. It means we need to solve the lasso only in single dimensions. Our multivariate problem turns out to be just a sum of univariate problems. People who want to know more about it, talk to me some other time, like now, for example. But the rest of you are finally free. Today I spoke about time frequency decompositions as one specific important example of a unitary transform. I mentioned that these are most useful in compression and denoising. And next week, we will take a completely different look at images, namely in terms of surfaces. So next week, we will look at images as topographic maps, as height maps. And this is a entirely different perspective, but one which allows you to do different interesting things. More on that next week.